I'm going to usually talk about the test particle as being small and positive. So when you have a particle with charge Q, let's say that is positive, the test particle is going to experience a force, and that force is going to point in what direction? The line that joins them determines that direction. If this is positive and this is positive, then the force points in that direction. Right? And in which direction does the electric field point? The force divided by the charge of the particle should be the electric field. Since the charge is positive, force divided by a positive number gives you a vector pointing in the same direction. So the electric field points in the same direction. Doesn't have to be the same magnitude, of course. If I put the particle in a different location, say over here, then the force on that particle would probably be bigger. And the electric field would probably be bigger. And so that's E over here. And this is F. So what does the electric field look like at all points in space? If this is a charge plus Q of any positive charge, then the electric field at this point, you can calculate it and find out that it points in that direction. At this point over here, it points in that direction. At this point over here, it points in that direction. Here, in that direction. Here, in that direction. It always points away from the positive charge. It's like a sea urchin, right? With all these spikes coming from the center. Right? So that is the electric field of a point charge positive. So imagine in this analogy with the wind, imagine positive charges as blowing this invisible electric wind, blowing it out. Right? So that's what you want to keep in mind about that. And if you do the same thing for a negative charge, what's the electric field in the neighborhood of a negative charge? I should use the other one. Actually, I'm going to use this one. So a negative charge, say here, you put your test charge here. The force is going to be, again, the test charge, as I said, is a positive number. So the force is going to be this way, attractive. And in what direction is the electric field? Same direction, right? Because the test charge is positive. So they have the same direction. So I should be a little bit more careful with this direction. It's supposed to point along the line that joins them. Okay, and if I measure the force on the particle over here, it should point towards the negative charge. And if I divide it by the test charge, I get the electric field. So it should also be pointing towards the negative charge. And if I do it over here, bring my test particle here, measure the force, divided by its charge, the electric field will point that way. And if I do it over here, it's going to point that way. So the picture of the electric field around a negative charge is like this. Maybe a little too close there. And when you get closer, your vectors are bigger. So the picture that I want you to keep in mind is a vacuum cleaner, the nozzle of a vacuum cleaner having little holes. Okay, so the vacuum cleaner is sucking in air, and the wind velocity at different points in that room where you're using this vacuum cleaner with the attachment that is a circle with holes everywhere, the wind velocity looks like this, right? And if you drop some dust somewhere near that vacuum cleaner, the dust is going to move that way, right? And the closer the dust is to the nozzle, the faster it's going to go in, okay? So the question, of course, for both of these cases is that because we have the force on the test particle being equal is just Coulomb's law, right? We're assuming, and that's the part of electrostatics, that's where the name comes from. Statics means we're assuming the particles are not moving, so we can use Coulomb in this case. So K times the charge, Q that you have, the test particle has some charge. You divide it by the distance at which you located the test particle. And that goes multiplied by the unitary vector r. So in this equation, we have assumed that the origin of your coordinates is located at the charge. Right where the charge is, that's where we put the origin. And if I place the test particle a distance r from the charged particle, then the force will be given by this equation, right? And therefore, when I divide by the charge of the test particle, I get that the electric field, which is defined as the force on the test particle divided by the charge of the test particle, will give you kq over r squared in the direction r unitary. So your particle is at the origin at a point in space defined by a distance r in that direction by the vector r. Then the magnitude of the electric field in that location is given by the absolute value of this, right? And the direction will be given by the vector r hat. And the electric field can be pointing in the direction r hat, that means away from the charge if the charge is positive. So if Q is positive, the electric field and r hat are pointing in the same direction, right? So we visualize that as arrows pointing away from the positive charge. But if Q was negative, then the electric field would have a negative sign in front, which means that the electric field will point in the opposite direction as the vector r hat. This is r hat, that is the electric field. They go in opposite direction, right? So the electric field points towards the negative charge.